Hi everyone. In our last video we were exploring our data set where we had Roche scaled FIM scores for 40 different people that were being measured over 18 different months of therapy. And we were trying to fit a model where we had random slopes and random intercepts, and then looking at how a person's AIS grade, whether they were C1 to 4, C5 to 8, or paraplegic, affected those slopes and intercepts. And ultimately, we decided to keep our more complicated model where we had not only random slopes and intercepts, but we had an interaction of AIS grade with the intercept and an interaction of AIS grade with the slope. So in that model, we might want to get more complicated as time goes on. We might want to choose a more complicated shape for the time variable, adding in quadratic or cubic factors to make it curvilinear. We could also add in additional fixed effects. We might even add in time-varying covariates at the time level. Right? So there are lots of different things that we could do to make our model more complicated, but we wanted to stop here and evaluate this model and specifically check some of the statistical assumptions of the model to get a better understanding of our data and dig a little deeper into the robustness of our model. So for these multi-level models, they have many of the same assumptions as a regular generalized linear model. So we're going to look at normality and homoscedasticity. But the key thing to keep in mind for these multi-level models is that we have residuals at both level 1 and level 2. Right? So at level 1, which is sort of the time level, we have 18 observations for each person. Our model is going to make a prediction at each point, and everyone has a real score at that point. So we're going to get a residual from the difference between the estimated value and the real score. At level 2, we're going to have a fixed effect for both the intercept and time, and then we will have random effects, which are the difference between that group level value and each individual's intercept, or the group level value and each individual's slope. So those are all different deviates or residuals that we want to keep track of and we want to analyze. And at level 1, we'll just have a lot more of them because we have residuals at each time point. At level 2, we have random effects on both the intercept and the slope, but we want to evaluate all of those, both the random error terms at level 1 and the random effects at level 2, to see if they meet our assumptions of normality and homoscedasticity. So the first thing that we're going to do is actually condense our data frame down in order to make it a little bit smaller and create sort of a subject level data frame where we have one observation per row. So this is going to be our level 2 matrix or our subject level matrix. And I want to talk to you a little bit about what we're doing in the code right here actually, because we're going to create an object called level 2 and we're going to assign to it the value of the summarize function and the group by function. And the summarize function is a function in R that essentially allows you to apply a mathematical function or a series of functions over some amount of data. And group by essentially breaks a larger data frame down into a set of individual variables. So it'll sort it by cases of whatever variable you want it to, and then it will apply the summarize values to each of those individual cases. So by using summarize and group by together, what we're essentially doing is writing a for loop and saying, okay, while or for subject I in the list of subjects, do this calculation. Do all the calculations we want you to do. Once all those calculations are done, you move on to subject I plus 1, do all those calculations. Subject I plus 2, do all those calculations. So this is just a quick and efficient way to write a for loop if you might not be very familiar with how for loops work. So first, we're going to group our data frame, right? So our larger data frame was called data, and specifically we want to group by the subject IDs. So we wouldn't have to do this by subject ID, but in our case, we want to go subject by subject in our data. And then we're going to take out the person's AIS grade. So we're going to create a variable called AIS grade in our new level 2 matrix. And that variable is going to take the value from the previous AIS grade variable, and specifically it's going to take the first value that it finds. So for each subject, it's going to look in the AIS grade column, pull out their first value. And what this will do, if we print this to the screen, is create a matrix now that is 40 rows by 2 columns. So we'll have all of our subject IDs, and you can see that each person now gets 1 row in this level 2 data frame. And we have their AIS grades. So subject 1 was a C5 to 8, subject 2 was paraplegic, subject 3 was C5 to 8, and so on. So this is the beginning of our level 2 data frame. We're going to have each subject on a row, and then we're going to have what group they belong in. Next, we're going to create some additional variables in here. So we want to add on the random effect of the intercept. So we can pull that out from our model using the ranf or random effect function. And we want the random effect for the year. So again, we'll pull that out of our conditional model using the ranf function. And now when we look at our level 2 model, we should have added 2 columns to this table. So you can see now we have subject ID, we have AIS grade, we have a random intercept column, and we have a random year column. So we have each subject, what group they were in, their random effect for the intercept, and their random effect for year. And once we have that in place, now we can actually check the statistical assumptions underlying these random effects. So first, we can use the QQ norm function to create a QQ plot. And we can do this for the residuals at level 1. So here we've done QQ norm of the residuals for the condition model. So you can see we have 720 of these little dots because we have a residual for each person at each time point. And this is roughly linear. It tends to tail off, down at the bottom. So, we might want to evaluate this more statistically using like a Shapiro-Wilk or Kolmogorov-Smirnov test. But whether you use the Shapiro-Wilk or the KS test, right, there are some trade-offs to that in terms of the sensitivity and the size of your data set. And the other important thing to remember too is that these linear mixed models are relatively robust to violations of normality. So I often will apply a more visual approximation of the data, and if the QQ plot looks relatively linear, and actually it would probably help if I made our X and Y axes a little more square, then we can probably evaluate this a bit better. But when this is a little bit more square, you can see it's not bad. If this had been a more substantial deviation, this might suggest something about our variable needs to change. We might want to transform our dependent variable, or we might want to adopt a different method of analysis that has different assumptions about the distribution of errors. Similarly, we can look at the residuals at level 2. And again, it doesn't really matter if you're at level 1 or level 2. The linear mixed model is relatively robust to violations of normality. And here you can see that it looks pretty good with the exception of one subject who has a very negative intercept here relative to the theoretical quantiles that we would expect. So this is a participant perhaps of some concern in this model. When we look at their slopes also, we get a little bit of this sort of deviation from linearity down at the negative end. And at the positive end, we have someone who has quite a bit higher slope than we would actually suspect from the theoretical quantiles. So we're going to also check these individuals in terms of their influence on the model. And this suggests that we might have a couple people who have statistically anomalous slopes and intercepts within our data. And then we might want to decide, okay, are those people who we should exclude for some reason, or is there a variable we haven't accounted for yet that might actually help fix those residuals? Because this is an analysis of the residuals, not an analysis of the data itself. When you add different variables to your model, that could give you a very different pattern to your residuals. So next, we'll look at homoscedasticity, and again, we'll do this at level 1 and level 2. So let's plot that, and actually I can pull this out. So homoscedasticity, as you might recall, right, is the assumption of roughly equal variance in your residuals across the values of the model. So here we're looking at level 1, so we're looking at each fitted value and the standardized residual at each time point. There is a bit of a taper off on the far right-hand side where we also have fewer of the more positive values, but by and large, this isn't clearly funnel shaped, where there's a really large deviation at one point that then tapers into very small deviations at the other end. This taper here in the upper range is a little bit concerning, but I think I would be more worried if we saw this really expanding out at the low end, whereas we see a relatively high variance across up until we get to about a fitted value of 80. Similarly, we can look at the homoscedasticity at level 2. So when we look at homoscedasticity at level 2, rather than seeing each individual residual at each individual fitted value, what we're looking at is the standardized residual for the random effect. So in this case, this is the standardized residual of the intercepts as a function of what group you're in. So in each group, which is a level 2 variable, we can see a box plot which shows us the distribution. So in general, these look pretty good. We see similar variability in the random effects across our groups, with the exception of this one person in the C5 to 8 group, who is also the person who was probably throwing off our QQ norm plots when we were looking at normality. This person has a much lower intercept than would be predicted by their group membership. And it does indeed seem pretty low relative to everybody in the sample, not just the people in the C5 to 8 group. Similarly, we're going to want to test this for our slopes. Now, when we look at the slopes, there's a bit more variability, it looks like, in the participants in C1 to 4. But overall, this doesn't look too bad. There's no extreme outliers for people in the random effect of the slopes, and no group is massively more variable than the others, at least based on sort of a visual inspection of these random effects. So that one participant's intercept is potentially a concern, and we might want to look at that participant's data and try to see, can we explain why that person has such a low intercept. Another thing we can do is to look for influential participants. There are packages in R that will actually let you calculate influence statistics like leverage and Cook's distance at both level 1 and level 2. We're going to do a more visual inspection of the data, where we're just going to look at the distribution of the residuals as a function of the subject ID. So this is at level 1. This is looking at all of the residuals for each subject. And this can help us get a sense of, are some subjects really driving the model and maybe pulling the model in one way or the other? And is our model really a good explanation of our data? And if not, then for whom is it not a good explanation of the data? So you can see that some subjects definitely have a tighter distribution and are better fit by the model than others, whereas other subjects, such as subject, I guess, let's see, this is subject 8. Subject 36 is a pretty good example. You can see that they have a very large distribution for their residuals. And you can see, a couple people are generally fit pretty well, but they might have a couple outliers in their data. And that's relatively normal. I think what we would be concerned about here is if we had anyone who was really, moving far away from zero and tended to have really biased to be overestimated or underestimated by our model, and we saw real differences. At the moment, it looks like there's quite a bit of variability around 0, and there might be a slight bias toward our model overestimating, creating these negative residuals. Similarly, we can look at these distributions by subject at level 2. So here we're looking at the standardized residuals for the random effect on the intercept. And you can see that in general, they all look pretty good. But if you recall, we had one subject in the normality case and the homoscedasticity case who was causing problems for our intercept, and it looks like they're right there, subject 13. So subject 13 is the one we might want to pull out and actually scrutinize their data in more detail, maybe even go back to the case notes and see if there's something, some other reason why maybe that subject is not fitting. Maybe they belong in a different, they're truly from a different population than the rest of the participants. And finally, we'll look at variation in the slopes. So here again, we're looking at the standardized residuals for the random effect of the slope as a function of your subject ID number. And we can see, again, it's a pretty nice distribution hovering around 0. No one is as extreme. Subject 30 here has a slightly higher slope, but in terms of the value for the standardized residual, it's not massive. So there are packages out there to allow you to calculate some of these things in more detail. For instance, you can get a Cook's distance measurement for a measure of influence for individual participants and individual data points in your model. But this visual inspection of the assumptions, I think, is an excellent starting point and something to help make you aware of the things that could go wrong in your model, and really trying to make sure that your model fits the data, right, rather than the data sort of bending your model out of position because you have one person who's massively different than everybody else. So I hope that's helpful, and in the next video we'll talk about expanding these models into curvilinear models where our time variable is going to get more complicated.